All right, welcome back. And so the purpose of these videos, this unit, is to talk about the periodic properties that we see of the elements in the periodic table. And we need to talk about some of the incredible diversity that we see within the periodic table. And this is what we're hoping to give rise to and have some of that conversation about. So here we go. We're going to start with effective nuclear charge. And so if we look back at Coulomb's law, when we look at effective nuclear charge, which is the basis for this, the equation here it is, F is going to equal K, Q1, Q2, divided by the radius squared. Okay, and so that's Coulomb's law. And what Coulomb's law tells us is that the strength or attraction or repulsion between two particles is going to depend on the charge of the particles themselves, that's Q, and it's also going to depend on the distance that those things are apart, that's R. Now, this K is a constant that we use to make sure that the math works, and that's how constants work in science. Somebody said, hey, we're going to throw together this thing, and we're going to put a little number in front of it to make sure that it works all the time. And that's really all that is, okay? Now, there is a bit of a complication to this, okay? Now, in the hydrogen atom, we only have one proton and we only have one electron. And so all we have is the attractive forces that are holding those two pieces together. Now, as soon as we move up an element in the periodic table, though, we're going to start talking about lots and lots of different forces involved and lots of different interactions between particles that are at play that interact and cause us to have problems with that. Okay? And so we have attractive forces between the electrons and the nuclei, the protons that are in the nuclei. We also have repulsive forces from one electron to another. And so these electron-electron repulsions negate some of the attractive forces that electrons feel towards the nucleus. And so we say that this decrease in attractive force between electrons and the nucleus is due to the screening of the electrons by other electrons. And so the fancy word here is going to be screening. Okay, much like your television set is a screen, screening, S-C-R-E-E-N-I-N-G. Okay, and so when we say that we're talking about electrons screening one another, what we really mean is that those different forces are kind of shielded by one another. They kind of hide some of those forces, and so that's what we're looking at. So to measure this impact, we're going to use the effective nuclear charge. Effective nuclear charge, which is indicated here by the ZEF. And that is what the effective nuclear charge is. And so because of the screening provided by other electrons, the effective nuclear charge is always less than the actual nuclear charge. And so Z effective here is always less than what we expect Z would actually be. Okay, now this being a chemistry class, there is an equation for this. And so that's what we're going to do. We're going to talk a little bit about that equation and see how that works out. So here we go. And so we can calculate Z effective, the effective nuclear charge, by finding the Z value minus the S. And so Z is the actual nuclear charge which is going to be your positive number from your protons and your negative number from your electrons, and go from there. And then S is our screening constant, and this is going to be a positive number. And it is usually close to the core number of electrons in the atom. And we do have other valence electrons screen fellow valence electrons a small amount, so the value of S is going to be varied a little bit. So that's going to be something that we're going to see change. Just a little bit. It's not a whole bunch, but it is something that is going to be a little bit different from time to time. And so I figured that we probably want to have a bit of an analogy here. And so if you give me a second, I'm going to move this up screen a little bit, and we'll be right back. All right, and so what we wanted to do was move this up a little bit to make it a little easier for us to see this. So here we are. And so what we're talking about as far as an analogy to understand what's going on here, when we talk about nuclear charge, let's imagine that the nucleus is going to be a light bulb inside a glass shaded lamp. Okay, now our nucleus is the light bulb in the middle, and so what we're going to talk about is the nucleus, and the force that the nucleus is exerting is going to be the light produced by that light bulb. Okay, our glass lampshade, those are our core electrons that are in the way of the way we would see that light, or the force from those protons on the outside of the core electrons. Okay, and so if we're going to change our analogy, let's say that we put a thicker glass shade. So if we put thicker glass shade on a light, but the light's intensity stayed the same, we would be actually having, in the real world in terms of the atom, we would have more core electrons being added. So that means S is an increasing number. So that means we're going up in atomic number, and we're adding more electrons as we do that. Now the impact on that factor is that's going to decrease our effective nuclear charge. Now imagine we put a higher watt light bulb in the center of that. That means that we're adding more protons to produce more force, but the glass shade stayed the same, and so the larger number of protons means that my effective Z value is going to increase, which is increasing my effective nuclear charge. We're going to use this analogy a couple of times here, and I hope that that'll help you understand the way these forces work and how some of this stuff works. Okay? And so the important point here is to recognize that the trend in the effective nuclear charge as we go from left to right in a period on the periodic table. And that's the goal here. And so that's what we're doing here right now. That's this. We're trying to figure that out. So the effective nuclear charge, the ZEF, increases from left to right across any period of the periodic table. The reason for this is that the core number of electrons remains constant from one end of the period to the other. As we move from one side of the periodic table over here by hydrogen and move back to that side, the core number of electrons inside the core stays the same. The valence level on the outside of that does change. We add more electrons to the valence, but that core number in the middle, our lampshade, stays exactly the same. Okay? Now, the number of protons as we move from right to left, so the valence number of electrons, the core number of electrons stays the same, but we're putting more protons on the inside of that. We're putting a brighter light bulb in as we work through it. And so what happens then is the nucleus is increasing, the protons in the nucleus is increasing as we go over from here to over here on the periodic table. And so any valence electrons that are added to that outer label as we go from there to there are ineffective at screening one another. So the positive charge is very inefficiently counteracted. And that means that the effective charge, the nuclear effective charge, increases as we go from over here to over here on the periodic table. And so to go along with our lamp analogy, the lamp is getting brighter while the shade is remaining the same. Thus, we see more light from the lamp. And so that is the gist of nuclear effective charge. I've got to go to the next page here, and we're going to do that. I should have paused it. I didn't. I don't know why. Okay, so the effective nuclear charge valence electrons field going down a column in the periodic table changes relatively little. Sorry, I changed my page on my notes too fast. Relatively little. Okay, and so those effective nuclear charge going down a group, down a column, doesn't change a whole heck of a lot. So what does that mean? Or that is to say that the effective nuclear charge increases slightly as we go down a little bit. We are adding many, many, many protons going from here to here on a family, but we are adding many electrons as well as we go down that group. And so the more diffuse core electron cloud is less able to screen the valence electrons from the nuclear charge, and so the value increases going down the column. Just a little bit though, not a whole heck of a lot. And so in terms of our analogy, to do that we're adding a brighter light, but we're also adding a thicker shade around that light bulb, and so the amount of light that we see is only getting a little bit brighter. Now, the important reason to understand the effective nuclear charge is because it is effectively the reason for many of the other things that we're going to talk about here in this chapter. Because of those forces and those interactions that are at play, we really need to understand how that works so that we can understand the other trends that we're about to discuss here and now. So that's what we got. So thank you, and talk to you again soon.